Hello everyone, it's May 24th. Alright, the voice still not 100% ready. But first of all, I need to address yesterday. So we didn't finish yesterday because I just couldn't continue. And afterwards I looked at the solution and it took me a long time to even understand the solution. That question is probably the hardest that I've ever done on LeetCode. So our intuition is correct. This is a graph. It's a graph problem, but the way that I build a graph is not the optimal. When I build a graph, the edge, the weight of the edge, when I build my graph, the weight of the edge is the length of overlap, right? Now, because of that, there will be edges with zero weight. And when I think if the edge has zero weight, then those nodes are not included in the graph. But apparently this is giving me more trouble because some of the nodes are not in the graph. I cannot really find the path in the graph that covers all the nodes. So the correct way to build a graph is to use the weight as the number of letters that needs to be appended to one of the letters. So if two words if one word has say 4 letters, the other word has 4 letters, and 3 of them overlap, then in the new way of building the map, the weight of the edge connecting these two nodes will be 1, because you only need to add one more letter to the previous one in order to reach a superstring that covers both. So because of this, all the edges have weights, because the question says that the given words, none of them can completely overlap the other. So at least there will be one letter that needs to be appended in order to concat two words. So the weight of the edge at least is 1, and at the most is the length of the second word. So now we can include all the words in the graph, and then it becomes a so-called traveling salesman problem, the TSP. So we have the graph and we have all the edges. It's a directed graph, and then the problem is just to find a path that connects all the nodes, travels through all the nodes, and then accumulate the least amount of weights, because the weights is the number of letters we need to add additional. So we want to add as little as possible. So just traverse through the entire thing and then find the path that has the least amount of weight. Now TSP itself is, according to Wikipedia, I read it a little bit. TSP is a very difficult problem. It's NP hard, doesn't have a polynomial solution. It does have a complete solution, but it runs in 2 to the n times n squared runtime. But anyway, now the problem is just to solve this TSP, and I have no experience solving the TSP, and the solution itself was quite marvelous. Actually, I want to share right now, just kind of give an idea how it looks like. So this is the solution after I read through the I wrote a lot. This is a solution I basically wrote myself after fully understand what the official solution is doing. So first of all, of course, this is the building the graph, right? And then instead of, so like in our previous version, we have this I in range, right? And we use the I, which is the number of letters overlap. But now we don't use I, we use the length of the second word minus the overlap. So just the number of letters that are going to be appended in addition to W1. So that's the graph. Nothing special about there. Now the thing special here, this is the real thing. So the intuition is we want to go through all possible states. The state is just a set of words that have been traversed, have been encountered. And then there are 2 to the n number of a word set. We can choose word 0, right, at the 0 position, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, right, and then 1, and then 1, 2, 1, 3, 1, 4, and then also 3 letters, 3 words, 4 words, so all of them. Now we want to traverse through all of them, and the goal is, if we're given a state, which means just a set of words, and we want to know if one of the words in the set of words is the last one added, what is the minimum length of the superstring? So we want to use this condition as our DP table, right? So basically, you can think of as the key of this DP table will be the state, the set of words, and the second key is the last is the word that's being added last. So there are 2 keys. So naturally, we'll think about, okay, 2 keys, that feels like a 2D table. But the problem is, how do we represent the set of words in a number? Now here is the genius part. We represent the set of number as a bitmap, right? So in a bitmap, if we do left shift n, right, then we have a bitmap of length n, and then we say any position, like each position represents the index of the words, and if that position is a 1, that means that word is present in the word set. So we can just loop through all of them, right? Loop through all of them, all of the possible set conditions, and then for each one we set up n. That means the n words. So this DP has the rows. Each row can have a key as the state, the set of words, and each column is the index of the word that is the last one that occurs in the encountered in the set. And initially set everything to infinity, because what we want here, the actual value, is the minimum length of the superstring that covers all the words inside this word set. So that's the basic of this DP. And we also need to have a path, because we want to memorize the path that actually leads to the final solution. And this path has a similar setup, but it means differently. So again, we have the first level of key is the state. Second level of key is the word that occurs the last in the state. But the value itself is the word that occurred right before the current word, right? The word occurred right before the current word. So basically, we can think of this as the parent, like the parent word before the current word. So by knowing this value, right, by knowing the current word, then we will know its immediate parent, and then we can keep doing this because we already know the immediate parent. And when we put the immediate parent into this table, then we know the parent of the parent. So by doing this, we can go step, 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 and a step back in order to find the final path. So this is to record the final path. And of course, we said the minimum length is global minimum length, and the global last node. So the path we want, the last node of the path we want. And the DP part is actually, if you think about it, it's not too complicated, right? So we go through all the states, all the set of words. And for each state, we go through all the nodes, meaning all the indices of the words, right? And then we find if this node is in the state. So that's just the genius part of using bitmap. We can just shift the state right to the right, I positions, and end with 1. If it's a 1, that means in the state, the bitmap, the ith position is a 1, which means this node exists. And we only handle it when it exists. So if it exists, then we compute the pre-state, right? So this is the state before node I is added because we say node I is the last one added to the current state. So we compute the previous state. Now if the previous state is 0, which means the word I is the first word, then we know the DP state I equals len words. That just means if we have an empty slate, we put one word in, then the minimum length of the superstring must be the length of the word. And then we continue. Otherwise, now we have a previous state. Then we need to find all possible nodes that could have been the word that occurs before the current one. So we go through a J, all of the nodes again, and you see we use the same comparison. So this is just to say if J exists in the previous node. If J exists in the previous node, then that J can be the parent node. And then we do the actual DP logic. So this is the actual DP logic. We say if J, right? So in the previous node, in the previous state, with J as the last node, we know the minimum super string length. That's that. And then we say we want to add I right now. When we add I, right after we add J, then the amount of additional letters added is the graph, is the weight of the edge. We add them together. If it's smaller than what current superstring length is for node I in the current state, then we update, right? Update the current state, and we also update the parent. We say the I's parent must be J under the current state. And this is just to check, right? If this is true, that means we have a state of 1, 1, 1, 1, 1, all once. So we have visited all nodes exactly once. And also if the current minimum length of the superstring is smaller than the global, then we record the global and we record the last node. So we run through the entire states, the entire 2 to the nth power states. And after we've done so, we will have a path. But the path is stored inside this 2D table. So we need to obtain the path by going through each state, right? So this is just to reconstruct the path. So we start from a 1, 1, 1 state, and then we know the last node because we always keep track of the last node. So we put the last node in the best path, and then we do current state minus 1 left shift last. So this one gives us the previous state, right? The previous state. And then also we update the last, and we see we save it to temp. So the path temp, this is actually current state. Last, this gives us the parent node of the last node. So we get a parent node, right? And then we go again, right? We go again. Every time we add the parent node into the best path, just pushing it into the stack, right? We're pushing to the end. And as we go through this, the current state eventually will get to 0, right? Because we remove each and individual node. Okay, so now we get a path after we go through this. Now it's time to construct the string. So because the path, the first node is the last element in the path, so we just start popping, right? So we pop the index, the pre-index, and then the starting result is the pre-index words, and then we pop everything in the path. Every time we pop it, we need to find the words. Words will be the current index, right? But we don't do the entire current word. We have to find the amount that needs to be added, which is the graph, right? So from pre-index to current index, that's the amount of letters, number of letters need to be added in order to concatenate those two. So we find the value, we do minus this gives us the tail portion of the word, we add it to the rest, and then that's it. So it is a massive effort, but it's worth it. It's worth it going through this. And this is a quite generic way to handle TSP. if something similar happens in the future, this can be the way to solve it. Okay, so that's the recap from yesterday. Let's try today. Hopefully it will not be too hard, so I don't have to talk too much. Alright, let's just take a look here. Nothing of concern. Let's do this to lowercase. Oh, come on, what happened? Alright, given a string s, return s after replacing every uppercase with the same lowercase letters. Okay, so I guess after yesterday's torture, they decided to throw us a very easy one. I think we can. Python has it. S dot to lower. If I remember, maybe it's just say lower. I'm not sure. I forgot. Yeah. So I mean, this is like a cheating method, so doesn't really mean anything, but it's fine. We're happy. Only 8 test cases. This is probably one of the easiest. So yesterday is one of the hardest, and today is probably one of the easiest questions ever. I mean, this is easier than FizzBiz, right? FizzBuzz. Okay, let's try to code it ourselves. Which is I don't think it's too complicated. So lowercase, that's awesome. It's going to be to check the Ascii table. I don't remember Ascii table. Where is the Ascii table here? Oh, that's not the one I like. Nope. No, Ascii, this one. This one's the one I like. There we go. So the difference is how much? 32, right? So this need to add 32. Everyone has to add 32. Okay, so we just say, we have 2 options. We can concatenate, or we can put it into, let's concatenate, right? So rest gonna be this, and we're just gonna say for lettering s, rest plus equal to letter if or letter is 97 to 122, I think. Yeah, 122. Else char or letter plus 32. Let's see. That's like the only requirement, right? Printable. Ooh, printable. I suddenly realize this might not be. Wait, can we like add this? What is Oh, so everybody else cannot change. Okay. Oh wow, that's not that. So if no, we'll just say if it's not 65 to 90. So 65 to 90, right? If not this, else if it is, then we do this and we return rest. Okay, let's follow up with what we do. Actually can do test case ourselves. Alright, this has to be this. All lowercase cannot change. Or uppercase needs to be ABC. That's about it. So do to lowercase. Huh. Why is that? I mean, question mark is outside, right? Oh, why you say, oh yeah, 65 to 90. Huh? Wait, do I have to do like parentheses? Hold up. If not, if odd letter is not inside 75 to 90, yeah, not inside 75. Oh, my bad. It's not 75, 65 to 90. 65. It's still not right. 65 to 90. Yeah, this is 63. It's not. We should do a letter by itself. Wait, what the hell? Huh? Doesn't make any sense to me. Yeah. $63, right? 63 is going to be false, so we should return a letter. What the? Yeah? Why? Why is it not working? That doesn't make any sense. Oh, wait. I thought it wrong. And this is wrong. Ha! That's like, didn't make any sense. Affecting my performance. Really poor. And it's like, why it didn't work? I got a test case wrong. Alright, this one should be right. Yeah. Anything else? Yeah, that's about it. Yeah, so this is compensation for yesterday. Compensation for yesterday. This is probably no. It's actually not that easy. I got confused by myself. This is pretty easy. ON, right? 28 milliseconds, 73% ranking. All right, I'm gonna just go through the gotta be a solution for this. Oh, the internet is slow today. Oh, there's no solution. I want to see. I don't think I've done this before. Maybe I have. It's too straightforward. I probably forgot. Nope. 709. 709. People don't like it. That's fine. No library method. Maybe we can do. I don't know. Like, let's see. Any smarter way? Ah, we can do that too. Yeah, we can do that too. That's true. We can do that too. Ah, that actually make it look enjoying. Yeah, yeah, I can do it that way. Have I done that before? No, I'm not. Alright, I mean, nothing more to say. Very straightforward. Good, good. We got an easy one, so I can shut it down right now and then keep recovering my voice. I'll see you guys tomorrow. Adios.